Okay, we are at 9:30, so I think we're going to go ahead and get started. So thanks everybody for showing up. We may have a few more trickle in, but as we are virtual, it's going to be much less obvious than people kind of sneaking through rows of chairs. They should be able to join quite nicely. So we can go ahead and get started then. So today I'm going to be talking to you about C++20's chrono, calendars, and time zones in MSVC, MSVC being Microsoft's Visual C++. That's where I work. I'm a software engineer on the Visual C++ libraries team. This is how you pronounce my name. You probably won't need to pronounce it very often, but for the sake of completeness, it is there as well. For those who are interested, if you want to catch up with the Visual C++ team later, we're hanging out in the Visual Studio channel on the CppCon Discord. We also have a survey down here where we are happy to get your thoughts and get some feedback from you. So check those out if you haven't had a chance to yet. We're happy to connect with everyone here. Okay, so before we really jump in, I want to just talk some logistics really quickly. So as questions come up during the talk, happy to take them. I'll kind of try to take them live as I can, where there are sort of natural stopping points. For those, please use the Q&A tab, which you should be able to find hopefully pretty easily at this point since we're on day 4 of the conference. If you want to raise your hand to ask a question, I'm totally open to that as well, but we're probably going to wait until after the full talk is finished to take those. But you can feel free to type in a question at any time. I will have slide numbers on every page. Hopefully the Zoom kind of option bar is not covering that up too much. So if possible, please reference the slide numbers, especially if it's earlier on in the presentation, just so I have an idea of what example you're talking about and so on. Okay, so just starting off about me, Miya Natsuhara. I am, again, a software engineer on the Visual C++ libraries team. I started in April of 2020, so beginning of pandemic. And so I've been on the team about 1.5 years. I'm also a lecturer at the University of Washington, focusing on their intro CS courses. So CS 1 and 2, as well as associated support courses for people just kind of coming to programming for the first time. I also have a very cute dog named Gumball, who may or may not make an appearance once he is up scratching at my door. But that's just a little bit about me. Okay, so what I want to talk to you about today, we're going to jump into a little bit of the development process just to give you some context on how we actually did all of this work. And then we're also going to do kind of a general overview and some examples on some of the major parts of C++20 chrono. And then where applicable, where it gets kind of interesting for MSVC's implementation, we're also going to be touching a little bit on some of the specifics that came up as we were working on implementing this feature, or really all of these pieces of this feature. But yeah, we're going to try to give you kind of an overview of chrono as well as some of the challenges that we encountered as we were working on it. Yes, I know I don't have a cat. I apologize. I have cats growing up, but this is my first dog. He's still pretty cute though. Okay. So just starting off with the development process here. So we did implement this feature along with pretty much all of our other C++20 library features in our open source GitHub repo, which means that you can go and look at all of the discussion and PRs and things like that were happening there. If you print out P0355, which is the paper that encompassed like really pretty much all of the changes. There were a few patch papers later on. It's about 75 pages long. It is a lot of work. So there's absolutely no way that we would have been able to finish all of this work on this timeline without the help of our contributors. So I'm calling out a few here who were particularly active on the chrono side of things over the last year or so and made really big contributions. So it really did take a lot of help from the community to get this up and running. As we were working with people, we also used a GitHub project to kind of track all the issues, different pieces of the feature, PRs, discussions, questions that were related to C++20 chrono. So you can check that out there if you're interested. It's not active anymore, but you should still be able to view it just to see kind of all the pieces that went into it, as well as like the 40 or so PRs that contributed to it. We also used a feature branch to do some development as we were, especially towards the end, as we were having a lot of people kind of pile on to get the final pieces of chrono in. So if you see that referenced anywhere, that was mostly there for that rapid development and collaboration, which we eventually, merged into main. But that's all there for your internet sleuthing if you want to look into it more. I've also posted a link here. We've been posting videos of our team's open code reviews to YouTube recently, where we just, in a Teams meeting, review an open PR from our GitHub and talk through everything going on, have people ask questions, et cetera. So the ones that are listed here underneath are ones that are specific to like working towards C++20 chrono. So you'll see things like clocks, sleep seconds, time zones, system clock now, and so on. So if you're interested, feel free to check them out. They're on YouTube publicly, and let us know what you think. Okay. On to calendrical types. This is going to be kind of the first general piece of chrono that I want to talk about. And it's kind of a nice intro to what chrono was trying to do here to give you an idea of all the different pieces that are introduced in C++20. So calendrical types, if you think about calendars, you probably think of days, months, and years. Chrono now has types for all of those things. But not only those, we have a lot of other ones as well. We have month day, we have weekday indexed, and some things that you might not expect to see necessarily, like something called year, month, weekday, last. This is only a subset of the types, the calendrical types that chrono did add. We're going to go through some of them. We're not going to really have time to go through all of them. Howard Hinnant, who was kind of the main person responsible for chrono, or these additions to chrono, has a lot of talks at CppCons in past times, in the in-person times, not the hybrid or virtual times. That goes into a lot of these in more detail, so feel free to check those out. But I want to give you kind of an overview of them and some examples. Okay, so starting off, I'm going to just start off with maybe the more intuitive, simple calendrical types here. So I have very short example program. You can see over here, I'm making a year. I'm giving it 2021, so that is this year. And because I have, I'm printing it out here, you can see when I actually get the output, it looks probably like what you would hope to expect. This prints out really nicely, really naturally, just because C++20 chrono integrates really, really nicely with std format, which is another C++20 feature. If you are interested in format, Charlie Bardo, another person on the VC Libs team, is going to be doing a talk on that later today. But because of our nice integration with format, we can print all of this to the output really, really easily and intuitively. And we don't have to do any crazy kind of workarounds to make it look nice or format it ourselves. So we can create a year, you can print it out. Cool. Hopefully what you would expect to happen. Down here, there's a couple things I want to touch on. So we have a month type. So we can create a month M. I'm using October here. So C++20 chrono includes a bunch of convenience type defs. So for all of the different months, you can just use their name and have it create, the 10th month in the year. You could also just use a 10 here if you wanted to, but if you want for, readability or preference or whatever you want, you can use those names. It's kind of a nice added thing to include. On the next line here, I'm adding months 3 months to the month of October. So slight distinction here, month is going to be a specific class type representing an individual month, whereas months with that S on the end is actually a kind of a chunk of time that I'm adding to it. So I'm not going to add like October to April, for example, but I'm taking 3 months and adding that to October to move it 3 months into the future. Okay. So there are a couple of things you might expect to come out here. Maybe we get a month of 13 because October is the 10th month and I'm adding 3 to it. Maybe we get some error because we're going off the end of the calendar year. But what chrono actually does instead is maybe the more hopefully intuitive thing, which is it does this kind of wraparound math where if I say it's October right now and I say in 3 months, I am going to go to the grocery store, hopefully I'm going before then. I'm really talking about January. So it does this wraparound math for you. And a big part of the design of chrono is to hopefully make it as intuitive as possible to actually work with. So if I add 3 months to October here, I do get January back out. Okay. All right, another example touching on some other simple calendrical types. So here I have a weekday. So similarly to the way that we have October as some convenience type defs in the names of months, we also have the names of weekdays. So I can say Thursday here, or I could have said 4 just as easily. Again, similarly, I can add 4 days to Thursday. It'll do that wraparound math for me again, and I will get back out Monday from here. And as always, we're getting some nice formatting through that chronat intersection, which is at least what my team calls the std format and chrono intersection, but I don't know if that's common terminology yet. In this next chunk here, we can, as I kind of mentioned, you can make weekdays using just ints, so 0 and 7. An interesting part of the design here is that both 0 and 7 map to Sunday. And this is just to try to accommodate different people who maybe prefer to kind of think of their weeks starting on Monday versus people who prefer their weeks to start on Sunday. So this is the one exception, like no other weekdays have multiple numbers mapping to them, but to try to accommodate both of those kind of systems of dates, both 0 and 7 are going to map to Sunday here. So if I print this out, I will get Sunday in both cases. Again, Chrono's trying to be able to work with people as much as it can to make it intuitive and work with you the way that you keep your time and your dates. This last one down here is a little bit interesting and maybe not super obvious what it is at first. So a weekday index takes a weekday, in this case Thursday that we created up at the top, as well as a 4. And this is just essentially representing the idea of a fourth Thursday of a month. That month isn't specified yet, that year isn't specified yet, so we can't get a specific day, month, year out of this, but this is just representing the idea of a fourth Thursday. So American Thanksgiving is on the fourth Thursday of November, and a weekday index is really, really handy in that case to be able to talk about it, since it's not on a specific day of November every single year. Okay, and when we print it out, we kind of get that classic indexing syntax with those square brackets. I don't know how else you might want to format this, but this is the decision that Chrono made. Okay, more examples. Now getting into some compound calendrical types. So before we had kind of individual things, now we have some new types that are combining some of the simpler types that we were dealing with already. Lots of stuff on this slide. I'm going to talk through it. Starting off, just making some years, 2021, which is this year, 2020, which was last year. And then underneath that, I'm going to make a year, month, day. This is a super handy type that just really pins down an individual date and time. And here I can pass in a year, a month, I'm using October again, and day of 28. So today is the 28th of October, if I've done this right and I'm where I'm supposed to be right now. And again, printing it out, we get the date fully laid out in this format. Alternatively, we have a month weekday, which is a little bit interesting. We don't have a year specified. We are just creating this using a month, in this case, November, just for kicks. And again, a weekday indexed, that fourth Thursday. And if I print this out, I will get this syntax out of it, or this output, this formatted output. November, Thursday, and again, that index 4. So again, we don't have a specific year right now. This is just saying the fourth Thursday of November. This is the idea that we're talking about here. If we wanted to add in a year, then we could be able to get a specific day out of it. But here, again, this is American Thanksgiving, and it's the easiest example I could think of that makes weekday indexed really handy. Down here, we have a month, day, last, which is, again, a little bit of an interesting type. And all I'm giving it is a month. So what this represents is the last day of whatever month it is given. So here we're talking about the last day of February. Again, don't have a year yet. We don't actually even have a day yet because the last day of February depends on what year we're talking about. So this is just representing that idea of the last day in a specific month. So down here, if I do add a year in, right? So I'm creating a year, month, day, last. So the names of these just kind of show what additional type information or date information it's storing. I can create that using one of the years that I created up at the top, and then that month, day, last. If I go and print these out, I'll say, okay, well, in year, month, day, last, leap, which uses 2020 as the year, the last day of February was the 29th because we had that additional day in February for that leap year. Whereas if I print out year, month, day, last, no leap, which uses 2021 as the year in that case, I'll get 28. So this year, month, day, last type is pretty interesting. It's pretty powerful. You can represent this idea more generically of having just the last day of a given month, but you can actually get more specific information out if you ask for it here. Okay. Moving on to yet another example that is going to make things even more intuitive for you, hopefully. So prior to this, we've been using kind of classic constructor syntax to make individual years and days and months, et cetera. But now we get into another area where Chrono really tries to flex its muscles in being really intuitive and easy to use. So Chrono adds some new literals. So 28D gives us 28 days, and 2021Y gives us the year 2021. And it also adds in this operator slash syntax. So there are a ton of operator slash overloads in chrono that it adds, because fairly often you're writing your dates out with, either month, day, year with those slashes in between, as we have here, or maybe year, month, day, if that's kind of more your style. So we can make a lot of different dates in these compound types with operator slash. There are pretty much probably every combination that you could reasonably want already exists. That operator slash overload is there. But now I can create the same date, which is today, in two different ways. Again, chrono trying to kind of match whatever format of dates works for you. And if I print this out, I'll get the same day out of it. Under the hood, the same exact type is created, but we're trying to work with you to just deal with things the way that you want to deal with them, write them out in the way that you're used to. So similarly, we can make a year, month, day, last, again, using yet more of that operator slash, more of those operator slash overloads. Here, I'm adding 1 month to October just for kicks. But what I want to call out here is that I'm using this last. So this is a const expr variable that is in the chrono header. So it already exists for you. And this is just indicating that idea of a last thing. So the last day in this year, month, day. So if you want to use this operator slash syntax and you're trying to indicate the last of something, you can just throw in last here and it will do the right thing. It'll kind of be that specific type that tells chrono that we're working with a month, day, last, or a year, month, day, last, etc. So if I print this out, I'll get 2021, November, and last. So something interesting here is that last, literally last, is going to be what's printed out. We have enough information at this point to get the day out if we wanted to, but chrono is also very, is designed so that it's going to store all this information and be ready for you, but it's for the most part just going to do the work when you ask for it. So if you want to get a day out, it's happy to provide that information, but it's not going to preemptively do that work for you. And that's one of the things that makes chrono really, really fast. Look more at Howard Hinnett's talks for even more details on that. Another type of compound calendrical type that we can create with operator slash is a month day. Again, probably somewhat intuitive. You give it the month, we give it the day, spits out October 28th. I will note that here I didn't have to use 28D to make that day type. In this case, if I give it a month, it's unambiguous on the next thing that I'm going to give it is a day, but there's nothing stopping me from using days here to make it even more clear. And then month, weekday down here where I'm giving it a month and a weekday indexed. We've already seen this type, just showing again, even more operator slash overloads that you can use. And we get out the second Wednesday of March in this case. Okay, so chrono is really cool. Hopefully is able to be worked with fairly intuitively. We have a lot of things created here, support for you to make things really naturally without too much extra syntax. Okay, just to give you a full example using these calendrical types, this is just printing out all of the Patch Tuesdays in 2021. So if you're unfamiliar with Patch Tuesdays, they occur on the second Tuesday of every month. And it's kind of when Windows shoves out a bunch of updates for everything. So we patch things up. So here, what I'm doing is I'm creating a target year of 2021. I'm iterating through, enumerating 1 through 12 of the months of the year. And I'm creating a Patch Tuesday for the second Tuesday of the particular month I'm talking about for this target year. I'm converting this to kind of a serial count of days to be able to get the specific day out of it. And then I am creating a year, month, day out of that. And then I print all of this out to the console, to std out. And this is what I get out of it. Okay, so you can go through and actually click through your calendar and verify that these are the second Tuesdays of each month. But this is essentially to say, if you were going to try to write something like this to calculate all of this without chrono, kind of from scratch, using unsigned ints to represent different things potentially, it would probably be pretty substantial. Whereas with chrono, it turns into something that I can put on a slide. So chrono actually is pretty powerful. And especially for these kind of interesting things like the second Tuesday of every month, where it's not a super regular occurrence, it kind of depends on the year. It can do all of this really, really nicely for us. Okay, so some examples with calendrical types. Let's get into why we are doing this. So the simple calendrical types, if you look in the standard, if you look in our open source GitHub repo, they're very simple. They pretty much store one value, like an unsigned int typically of like, this is the year I'm talking about, or this is the month I'm talking about, or this is the weekday, etc. And like, what's the point? They're very simple. Why couldn't I just use unsigned ints for everything? You could. So there's no reason you can't do that really, but I claim that it is better. It is improved by the fact that Chrono provides these types for us. So thinking about our example from before, when we were using kind of the first example of those operators / overloads, if I didn't have the day and year types, we would just have those plain ints, so 28 and 2021. And maybe we don't even have October as a convenience type def. We're just throwing in 10, 28, and 2021 here. You can imagine if we're trying to like move these things around and work with them, maybe they're all smushed together. Maybe they're completely separate ints that are moving around. It would be very easy to accidentally treat the month as the day or the day as the month or something like that. And the type system wouldn't be able to help us out and clue us into something going wrong there. What we can do instead with this type system is ensure that we are dealing with things in the way that we intend with a lot more intention here. We let the compiler do some of this work for us and kind of double check us. So having these simple types improves type safety because we can make sure that we are interpreting these values as they are intended to be. So these calendrical types may be simple, still really, really helpful. Additionally, we get some nice abstraction out of here. So yes, we could just represent these values with unsigned ints or whatever kind of underlying data we have there, but we get a lot of abstraction here. Whereas now, instead of having to worry about doing that individual wraparound math for adding months to a month or days to a weekday, etc., having to worry about how to format every single little thing, we can actually just be the clients of them and have them exist and be worked with fairly intuitively. Plus, in reality, because these types are so simple, they often end up boiling down to constants anyway. So you get a lot of the benefits from having these types in the readability factor. You don't end up paying a ton of the cost. This library is very straightforward in a lot of ways, and the optimizer can do a lot of work for us. Okay, moving on from calendrical types, let's get into even more fun stuff, which is clocks. So first of all, what is a clock? So in Chrono, we have this new notion of a clock in C++20. So for a given type T to be a clock, it has to satisfy some conditions. I need to be able to ask for its rep, period, duration, and time point. And I also need to be able to ask whether it is steady or not. And I should be able to ask for what time is it now? So this kind of the requirements here and this notion of a clock is new in C++20. So we also get a nice type trait out of it that just checks all of these things and makes sure that, it reports whether a given type is a clock or is not a clock. So given all of this, to kind of contextualize it, I can create my own clock here. So I just specify my rep, my period, my duration, my time point. This is just an example. You could use a lot of different things here. I just decided that my clock is not steady. For exactly what steady means, feel free to check it out in the standard or CPP reference or elsewhere. And I should be able to report what time it is now. This is just empty because all I need to do is make sure that it's a valid thing to be well formed. So it is here. This does actually count as a clock, even though it's a fairly useless clock right now. Okay, so static assert is clock B does evaluate to true. So clocks are a thing. This is how you could make a clock. These are the things that make a clock a clock. But in reality, you probably won't have to make one of these for yourself because Chrono adds a lot in for you. So prior to C++20, we already had system clock in existence. But in C++20, we also get UTC clock, tie clock, and GPS clock. So file clock down here is kind of in both camps because essentially in C++20, we got a new way to refer to file clock. We got a using file clock equals stood file system file time type. So stood file system file time type already existed. So the guts were already there. In C++20, we basically just got a new way to refer to it. So kind of new, kind of old. But we have a lot of new clocks in C++20 that you can use for all of your time-related desires. We'll get back to this in a moment, But UTC clock, keep your eye on it. It's the only clock that tracks leap seconds. If you don't know what leap seconds are, stay tuned, it's okay. But UTC clock is a little bit special in this particular way. So we have a lot of different clocks. What is the point of them? These clocks differ in a couple of ways, so I just wanted to kind of compare and contrast with you for a moment. So UTC clock and system clock share the same epoch, January 1st, 1970, pretty classic. And those both track UTC or GMT time, so Coordinated Universal Time or Greenwich Mean Time. The difference here, as I just mentioned, UTC clock tracks leap seconds, whereas system clock does not. TAI clock or Thai clock, on the other hand, has a different epoch, January 1st, 1958. And this tracks international atomic time, which uses a weighted average of many atomic clocks to track time. So kind of a different time tracking system. Whereas GPS clock, again, a different epoch, first Sunday of January 1980, which happens to be January 6th. And this tracks the time maintained by GPS satellite atomic clocks. And neither Thai clock or GPS clock tracks leap seconds here. File clock is unspecified just because it's kind of tied into the file system. It is often going to depend on your OS to work with the file system nicely. So typically on POSIX, the epoch is January 1st, 1970. Typically on Windows, January 1st, 1601. I will say that is the case for ours. And it's used to create the time point system for file time type, as I mentioned. Again, unspecified whether it tracks leap seconds. Windows leap seconds story is just a little bit complicated, so I'm going to hold off on that for a moment. But because these are all kind of different systems of tracking time, like we didn't just make up Thai clock or GPS clock. If you Google these things or Bing these things, you'll actually understand a little bit more about what they are and why they're separate from each other. But depending on your program or application, maybe you want to use one clock versus another clock. So we have all those different options. I will say probably by default, system clock and UTC clock are kind of the best go-to clocks if you're not really sure where to start. Okay, clocks aside, now we have this local T thing. So local T is not a clock. It doesn't satisfy all of the requirements for being a clock. It's kind of a pseudo clock. It's treated like a clock in a lot of ways, but we can't ask what time is it now. So it doesn't quite meet the clock requirements. This essentially is meant to represent a time without like qualification of a specific time zone just yet. So just saying 2:30 a.m., which is kind of immediately a red flag for all of us maybe working virtually these days with lots of different time zones. Like it's like, okay, 2:30 a.m. where? So local T is just meant to kind of be that time independent from that time zone for the moment. It doesn't seem like it would be very helpful just yet, but we'll get there soon. So just kind of hang on to that for a moment. Clock cast is something else that we have now in C++20 chrono. Because we have all of these different clocks that have slightly different ways of kind of tracking time or, when their epochs are, we can cast between them. So the library does this for you. It takes into account the epochs of the source and destination clock, as well as whether they track leap seconds. Remember, UTC clock does, while everything else doesn't, with like a asterisk, maybe unspecified on file clock. And internally, it uses clock time conversions, and those use to UTC, from UTC, to sys, and from sys. That's more kind of under the hood. If you want to look more at that, feel free. But if you just want to use clockcast to convert things along, you can do that. You'll probably need to have those to and from UTC and sys functions kind of in place if you're using your own custom clock, though. Okay, leap seconds. I've talked about it a couple times, and you're probably curious at this point if you're not familiar with what they are. So let's just dive in a little bit and get some background on what leap seconds are. So a leap second is a 1 second time adjustment that is occasionally applied to UTC time to accommodate discrepancies that develop between precise time and observed solar time. So precise time being the thing that just kind of ticks forward regularly that we think of as time, and observed solar time and like actually like what the Earth is doing with the sun and stuff like that, if we need to kind of make that adjustment every once in a while. So these are all the leap seconds that have occurred ever. So this is just a table off of Wikipedia that I reformatted into a nicer table. So you'll notice that one, they're not regular. They're not regularly dispersed. Like we don't have a leap second in 1980, for example. And sometimes we have two in a year. I think only 1972 has had that at this point, because I think when they realize like, oh, we need leap seconds, they're like, okay, we have some catching up to do. Let's make this adjustment and kind of lean into it. And they happen either on June 30th or December 31st of every year, but like, there's no guarantee it's going to happen. We have to check out what's going on astronomically at that point. Okay. So interestingly enough, there are two kinds of leap seconds. There's a positive leap second where you insert an extra second. So if you're looking at a clock, it might read 58, 59, 60, and then 0, whereas typically it would just roll over to 0, 0 right away after 59. And there are also negative leap seconds where a leap second or a second is removed. So if you're looking at a UTC clock again, it would go 57, 58, and then directly to 0, 0. So just kind of like that 59 second just doesn't exist anymore. Interestingly enough, there are only +1s in this table. So the only kind of leap seconds that have happened so far are positive leap seconds or leap second insertions, where we insert that extra second to kind of realign with the sun or something. Negative leap seconds haven't occurred yet, so there have been no leap second removals, but they theoretically could. And at least Charlie Bardo thinks that there might be one coming up soon. So keep your eyes out for that. It will be monumental. I'm sure it will be front page news everywhere because everyone knows what leap seconds are. So as an example of what you might see on a clock, this is just a little clip of showing 58, 59, 60, and then 0, 0. I will note this is an artificial leap second that was inserted for the purpose of making this little clip. So you'll see in the table, there's no leap second that has happened in 2018. This is completely artificially inserted. It's also not on June 30th or December 31st. But just for the sake of understanding what might actually happen on your clock if you are anticipating that leap second and happen to be looking at your clock right at that time. All right, background on leap seconds. Let's jump back to clocks for just a moment, because I want to just provide a little bit more context now that we know what leap seconds are. So to give you an example using that clock cast, where we can take a clock over here and convert a time using that clock to a time using a different clock. This is using our TIE clock, or International Atomic Time clock. And I'm saying, hey, what time is it now? And I'm storing it in a TIE time, which is just a time point, a point in time that's related to a TIE clock. If I print that out, when I made this example, it was October 19th at 1:13:06, point blah, blah, blah stuff. Now, if I want to say, okay, take that point in time that references a TIE clock, and clock cast it to a UTC clock, we actually get a different time out of here. We have a 37-second discrepancy, which might seem weird because time should be time and what's going on. But we can actually kind of dig into what's going on here. So first of all, there's a difference between the TIE clock and UTC clock epochs. So there's an initial discrepancy right when they are first born into existence of 10 seconds. So this is explicitly called out in the standard, just because because of the epochs being different. Additionally, remember UTC clock is the only clock that tracks leap seconds. TIE clock does not. And there have been 27 leap seconds that have happened in our history so far. So there's an additional 27-second discrepancy that's introduced just from the leap second angle. So this gives us a 37-second difference total. So this is just combining that 10 seconds and 27 seconds. So you can already see how clock casting is actually very, very helpful because it can take all of these things into account. You don't have to go and look up what the epochs are for these individual clocks or what tracks leap seconds or how many have happened. It'll do all of this work for you. But this is an example, both using leap seconds and clock cast to give you an idea of how to kind of start working with these things. Okay, jumping back to leap seconds, just wanted to take a second to contextualize what was going on. Okay. So leap second story in MSVC. It's super fun and complicated. So this is kind of the first time when we were working on implementing things where we were like, ooh, okay, got to get a little creative here in terms of how to actually implement this. So let's dig in. So previously, the Windows operating system did not keep track of leap seconds at all. This does not mean that Windows was just off by 27 seconds in time with the rest of the world. It just means that they weren't tracked individually, but whenever the OS would periodically like kind of sync up its time, it would notice it was behind and it would make adjustments. But as of Windows 10 October 2018 update and Windows Server 2019, now the Windows OS is going to keep track of leap seconds. But because this like only started in 2018, it's not going to like remember any leap seconds from before. Okay. So this was great news because we had a way to actually detect when leap seconds were coming up, because as you saw on the table, we can't really anticipate exactly when they're going to be coming, but we want to be able to handle the case where a new leap second is inserted or potentially removed if we get a negative one, just as our library exists in the world. So the way that we do it is we read post 2018 leap seconds from a Windows registry. This is the Windows registry if you are interested. So when a new one comes up, it turns out there haven't been any leap seconds since 2018, but when one comes, we should be able to detect it. And then for those pre-2018 leap seconds, that big table of 27 leap seconds that we had on previous slides, we're just maintaining a static const expert table to pull that data from. That is not changing. We're not retroactively inserting leap seconds years back or anything like that. So we can still look up that information really, really easily. Note, we don't currently have a way to detect upcoming leap seconds on older Windows OSs. Ideally, we'd love to be able to implement this for all OSs, regardless of particular version, but we have kind of technical limitations here. But because leap seconds happen pretty infrequently, we're going to kind of keep our eye on it. And when a new one comes up, we'll add it to that static const expert table. So even older OSs will be able to detect that a more recent leap second has happened. They'll just need a library update to get that information. So this is kind of the best we can do right now, but we're keeping our eyes on and we'll try to continue to think about whether we can do better. All right, so if you're interested in learning more, a lot of this information actually came from these two specific blog posts by Dan Cuomo and Daniel Havey. Way more information in here than you would probably need to know, but if you're interested, the links are in this slide that will be posted. Okay, last chunk here, time zones. So this is a hefty chunk, to be fair. This is where things get really, really interesting if you weren't interested enough after leap seconds. Okay, so chrono, a very big part of it, it now includes an interface for accessing the IANA time zone database. So that's a database of time zone information and history that is very, very reputable and considered very standard. And in true C++20 chrono form, it adds a ton of new types to the library. These are just a couple of them, but we'll talk through, I think, at least the ones on this slide. So starting off, perhaps the most intuitive one, time_zone. So this represents a time zone and all time zone transitions for a specific geographic area. So America, New York, I'm in America, Los Angeles right now. And this is, so it represents kind of what you would hopefully think of as a time zone. So this stores its name as well as details like its actual UTC offset and whether it's starting like a daylight saving time zone or not. As opposed to a time zone, we have a zoned time, which is related and similar, but not the same. So this represents a pairing of a time zone and a time point. So this is giving a specific point in time in the context of a particular time zone. So this is where we get into not just 2:30 a.m., but 2:30 a.m. Pacific time or something like that. A zoned time can produce a local time or an equivalent sys time. We haven't explicitly gone over what those two things are, but we will in a moment. But essentially, this is, again, local time talking about a point in time that's not associated with the time zone. So if you just wanted to get the 2:30 out of there, you could. Or sys time, which is related to UTC. So it is a literal point in time, no weird daylight saving transitions or anything like that. Okay, sys time and local time. This is what they are. Sys time is a time point that's talking to a system clock, whereas local time is a time point talking to that pseudo clock, which is local T. So conversions between sys time, again, that UTC timekeeping mechanism. It's confusing to talk about sys time as UTC because there is a UTC clock and UTC time, but like capital UTC, the coordinated universal time. And local time, they're usually pretty uncontroversial. This is just that regular time zone math that you're doing when you're talking to someone on the East Coast or over in Europe or in Asia. But there are a few cases where things get tricky. And spoiler alert, it's all daylight saving time's fault. So if you were in love with daylight saving, I'm going to try to convince you otherwise. So a lot of words on this slide. I'm going to talk through it all. I also have some additional kind of diagrams to hopefully clarify the situation here. But there are essentially kind of two cases where a local time to a sys-time conversion can cause some problems. As I said, it's all because of daylight saving time. So first one, we could get an ambiguous local time exception thrown. And this happens when there's a daylight saving time transition where there's an extra hour inserted. So this is typically that kind of fallback daylight saving transition where you get that extra hour of sleep maybe, but everything else in the world is kind of messed up. So when that happens, you get that extra hour inserted. That 1 hour block basically happens twice. That 1 hour block, if it starts at 2 a.m. to 3 a.m., that 2 a.m. to 3 a.m. block happens 2 times because you get that extra hour inserted. So if the local time that you're asking for, like 2:30 a.m., happens in that period of time, that period of time kind of happens twice. So there could be the first time you went through it or the second time, that's that hour that got inserted. So unless you specify, there's an enum choose in the chrono header as well now that says like, do you want the earlier version or the later version? If you don't specify that, chrono's like, I don't know what you want, and it's going to throw this ambiguous local time exception. Alternatively, if you think about the other kind of daylight saving time transition, when an hour is lost, which is that kind of spring forward, usually happens in the spring, a whole hour just kind of is removed from the timeline. So if you ask for a time inside of that hour, we're not going to know what to give to you because it doesn't actually exist according to daylight saving time. Okay, there's a lot of words there. Let's talk more specific examples. So an ambiguous local time exception, here is an example. So Sunday, November 6th, which is the first Sunday in November 2016, that is when the US fall daylight saving time transition happened. It happened specifically at 2 a.m. So I am picking a time at 1:30. This is the turning your clocks backward at 1 hour. So it went kind of time traveled as normally up until 2 a.m. And then at 2 a.m. it rolled back and was apparently 1 a.m. again. So we're going to get that 1:30 time happening twice. And you'll see that we actually catch this ambiguous local time exception that gets thrown when we try to actually pair it with the time zone, because American New York does have like daylight time or standard time versions. And this is the output that we're going to get. It's going to say, hey, this time you ask for is ambiguous. It could be this time UTC, or it could be this time UTC. It could be the daylight version of this time zone or the standard version, and we don't know what you want. So it's going to be ambiguous and we're going to complain here. So here I have kind of like two little ticker tapes of time just clocking along. Clocking along is a very bad pun. There's so many puns in time, in chrono and time when you really try, or even when you're not trying. So UTC time just keeps going normally because UTC time is simple and easy to understand. Whereas American New York down here we line up nicely with UTC. Here we line up nicely with UTC. We line up nicely 1 a.m. to 2 a.m. the first time, but then we do this thing where we start rolling back. So while UTC just keeps going forward, American New York jumps back, and now they're kind of moving forward like this. You can see that both 5:30 UTC and 6:30 UTC both map to 1:30 in American New York, depending on whether it's the first time through this hour or the second time. So this is an example of where an ambiguous local time exception would be thrown. Alternatively, let's look at the other kind of exception. We have a non-existent local time example here. So looking at the the springtime, spring forward daylight saving transition in the US. In 2016, that was on Sunday, March 13th. And I'm choosing very specifically 2:30 a.m. Okay, so at this time at 2 a.m., clocks were turned forward 1 hour. So it went from 2 a.m. immediately to 3 a.m. without having any amount of time pass in the middle. So this is another daylight saving transition. And we are, once again, I pair it with American New York. I get a non-existent local time exception. And again, if we look at our ticker tapes here, this maps really nicely, UTC to American New York, this maps really nicely, this maps really nicely. But once we hit 2 a.m., 6 o'clock UTC is great, but 6:01 UTC is now apparently 3:01 American New York. So this entire time right here just does not exist in this time zone. So if I ask for a time in there, it's going to be like, what are you talking about? That point of time did not actually happen. So we'll get a non-existent local time exception. Okay, so this is an example, hopefully, to make this a little bit clearer. First of all, how daylight saving time is super fun depending on your definition or sarcastic nature. And two, just like, this is when these actual exceptions, this is when it comes up. So not all the time, but sometimes. Usually the conversions are fairly uncontroversial. Okay, so outside of that, how do we actually get this data? We have another data type called TZDB, time zone database. And this is where we actually get all the time zone information and the names and when the transitions are and things like that. It has a version because we're dealing with data, updates could happen. So we have a version here. We have a vector of time zones. We have a vector of time zone links, which are just alternate names for time zones. And then we have a vector of leap seconds. So the IANA database should also be tracking leap seconds here. It also has some member functions. You can ask for like, hey, what is my current zone, depending on the OS that I'm using? And can I locate a zone given the name of a time zone? So if I pass in America, New York, it'll give me the time zone object for America, New York, or the time zone object pointer. Okay, so to get a TZDB, you can use a TZDB list. Because we could have different versions of the time zone database, we can have a list of them. This is mostly for like kind of long running programs where there might actually be updates while it's continuing to run. You can get a TZDB list with this get TZDB list function, very nicely named. It's a singleton, so you should just be able to grab that. And then you can iterate through it if you want all the different versions. But if you just want the TZDB, the like most updated that you have, you can just use get TZDB, which just basically gets the front of that TZDB list. So once again, an example of what that might look like. Here, I'm getting the TZDB through get TZDB, that chrono function. And I'm just getting out the zones vector of time zones from the TZDB, iterating through and printing them out. So there's way more output here than could possibly fit on this slide. But if you go and do this yourself, you'll get quite a number of time zones because they're going to be across the world. This is an example of how you could actually get the time zone database and work with it. Okay, so now, where do we get this data? The standard describes these facilities as interfacing with the IANA database. Great. The IANA TZ database is shipped with Unix-like systems. You should be able to find it here at this path. This is the case for Linux distributions, Mac OS, and some other Unix-like systems. But in true form, not so much for Windows. We actually don't have the IANA database shipped with our system, unfortunately. So what is the MSVC story for time zone data? Yet another time where we had to kind of take a step back and get a little bit creative. We had a few options to try to move forward. We could ship the entire IANA time zone database with the library. We could try to figure out some kind of networking scenario to pull in that data when we need it. Or we could try to find an alternate source for the data here. So what we ended up doing was, okay, shipping the entire IANA time zone database, maybe not the best idea. First of all, it's huge. It's 1.25 megabytes, which is more than twice the size of the STL's DLL. We would have some very unhappy customers. Plus, it would be a static kind of snapshot of the data. And as we've talked about, like new leap seconds get inserted, not all the time, but sometimes, fairly-ish frequently. Time zones change names. Some time zones decide, what is this daylight saving thing? I don't want to do it anymore. And updates need to happen. So if we just kind of packaged it up and shipped it with our library, we would have to worry about how to actually get those updates to customers. Networking, we don't really have anything that requires networking in the STL right now. We'd really like to avoid adding that requirement. So this didn't seem like a super great option either. We ended up finding an alternate source for the data. So that alternate source is the ICU library. So this ships as part of the Windows 10 operating system. Again, super great news. So the ICU data, it's not completely equivalent to the IANA database, but it's derived from the same IANA data. So it's pretty close. It gets us most of the way there. And this is actually available to us through the operating system, which is a huge, huge plus. We'll be able to receive updates to the time zone data through OS updates and through Windows Update, maybe on those Patch Tuesdays. And so we don't have to worry about having that kind of static image of what the data looked like. At one point in time, we can actually receive those regular updates with time zone renames, etc. Big asterisk, once again, unfortunately, the ICU library in a form that's digestible for us is only available in more recent Windows OSs. But as before, we'd love to be able to provide this information for all versions of the OS, but right now for technical limitations, this is where we are. We are investigating implementing a fallback mechanism for earlier versions of the OS. Okay, so differences between IANA versus ICU time zone data. So the IANA database defines standard and alternate names. We've kind of talked about this already, time zone names versus the time zone links. Whereas the ICU defines canonical and non-canonical names for time zones. So slightly different verbiage, and it turns out the sets don't quite match up. IANA also has a few older, somewhat abnormal time zones. Like, I don't know if you ever knew that EWT, which is Eastern Wartime, existed as a time zone because it only existed in the 1940s for a few years. But IANA is very, very thorough, and it does have that information there, whereas the ICU doesn't. IANA also contains the time zone renames that are from like fairly recently changes within the last year or two, whereas ICU, it looks like, has slightly outdated data, but there are very, very few discrepancies. So getting into the standard versus alternate and canonical versus non-canonical names, unfortunately, there's no easy mapping. Like, some standard names, according to IANA, are non-canonical for ICU, and some canonical names in ICU are alternate names in IANA, and there's no easy mapping between these two systems. So what we decided to do is essentially consider all ICU time zones to be time zones, time_zones. So essentially, when you go and interface with our version of the chrono header, what is going to be considered a time zone is a strict superset of what the IANA database would consider to be a time zone. So you should still be able to find everything in there that you want, plus a little bit more. And the only exceptions being the few ones here, like Eastern Wartime and those like very recent renames. This is kind of the system that we determined would be potentially best for us. Okay, given that, this is hopefully a nice overview of all of the different pieces of chrono. You have some insight into all of the fun challenges that we encountered as we were implementing it for MSVC on Windows. But your takeaways here are hopefully C++20 chrono is super, super cool and has a ton of new stuff. This is very honestly a surface level overview. There's a ton of stuff in there. The design of the library presented some challenges for Windows, but we made it work. We are working on improving it even more potentially, but we have it working on at least more recent OSs very nicely. And most of the library is still available to even older versions of the OS. It's only those leap seconds and time zones that get a little bit tricky. And time is so much more complicated than you could have ever imagined, especially leap seconds and especially daylight saving time, and probably some other stuff too. I had no idea how much I didn't know about time until I started working on this project. So hopefully you have some insight as well. Maybe you'll go and look into it a little bit more. On that note, I'll take some questions now. One of them I see from Jimmy in the Q&A tab. MSVC Discord channel, is that coming later? We're actually under Visual Studio, so you should be able to find that. I think you have to look at a specific other channel and like join the Visual Studio channel from that before it shows up. I don't know if I can troubleshoot that immediately with you, but if you post in the Discord somewhere, I'm sure someone can help. But yeah, it's Visual_Studio, not MSVC. No problem. We also have a question from Javier. Regarding leap seconds, are they inserted at the end of the day, beginning of the day at noon? As a follow-up, are they updated via an update in Windows? So they are actually inserted at a specific time. I think it is, I'd have to look it up again. It's like on the hour, and I think it is either at midnight or in the early morning. Sometime, I don't know, my daylight saving time in the US at least always picks 2 a.m. for those transitions, but I have no control over that. So it is at a specific time, a very predictable time. I don't remember exactly what it is, but you should be able to Google it. And then as a follow-up, are they updated via an update in Windows? So with the more recent versions of Windows, you should be able to have it already be detected. It should just show up kind of live. If you're working with an older version of Windows, it's only going to kind of recognize that a leap second happened when it does that kind of regular sync up to make sure that it's on track. So it's not going to necessarily show it at the individual like exact second where it's inserted, but it will get back on track soon afterwards. Leap second is simply a count that is added to a number of seconds to a given entity, day, month, year. Kind of. Yes, there is a lot of magic and really complicated date algorithms that we are very grateful to Howard Hinnant for publishing that detects leap seconds, because there actually are a lot of very complicated rules around them. And then there's also leap days, which are separate from leap seconds, but also have complicated rules. Yeah. How does it handle time jitter? I'm not sure I understand time jitter. If Philip wants to raise a hand or unmute or clarify the question, I'm happy to give it a try though. Philip is on mute. Uncertainty around a point. So actually, I'm not super familiar with the concept of time jitter, which also means that Chrono is probably not familiar with that concept either. Chrono has a lot of mechanisms in place to deal with the kind of predictable things that are going to come up. So random, they're not random. They're regular leap days according to very specific rules. And we can receive updates and information about when those leap seconds happen. But uncertainty around a point, Chrono is very, very precise. So it has time move along as expected. I could look into how time jitter might affect it or what might happen depending on uncertainty around a certain point in time. But I don't think that Chrono is trying to handle that in any sort of specific way. Question, what is the behavior of Chrono C++20 on older Windows platforms without the ICU lib? What problems may we observe? It's essentially just going to fail to compile, I think, because it's going to go and look, actually, maybe not compile, maybe you'll get an exception when you run it. Essentially, it's going to go look for those functions, those ICU functions where we can actually access that data, and it's not going to be there. Yeah, unfortunately, it's better than getting incorrect information or something like that. Like, it's just not going to work in the first place. So it'll be very obvious that, hey, I just can't do this with this version of Windows. But you're not going to be getting like some random numbers where it seems like it works, but it's just totally wrong information or something like that. It will be very obvious.